Good afternoon, dear students. We have a new topic to discuss today, that is thermal properties of matter. So, in this chapter, we'll first study about heat. We all know that heat is a form of energy, and this heat energy is due to the movement of molecules present inside a material. So, a molecule, maybe if we take a gas, there will be molecules, and these molecules will be having kinetic energy and they will be in motion. So these molecules can have a translational motion, it can have a rotational motion and a vibrational motion also. So the total energy, the whole total energy due to all these, that is translational, rotational and vibrational motion, this total energy is called the heat. And heat is expressed in different units. One unit is calorie. This is a CGS system of unit, and the SI unit is joule. And we know that 1 calorie is 4.186 joule. This SI and CGS relation is 1 calorie, that is 1 CGS unit is 4.186 joule. A similar term is a temperature. It is a quantity that decides the direction of flow of heat. We know that heat flows from a hot body to a cold body, and this temperature decides the flow of heat. It's actually the average kinetic energy possessed by the molecules of the body. So it is the average kinetic energy possessed by the molecules in the body. So the heat we defined as the total energy, total kinetic energy. Temperature is the average kinetic energy. Temperature, we know they are measured in different unit, for example degree Celsius or Fahrenheit or Kelvin scale. Even we use a Romer scale, R, that is a Romer scale. So degree Celsius, Fahrenheit and Romer or Kelvin. The SI unit of temperature is Kelvin. The standard unit of temperature is Kelvin. There is a branch of physics that deals with the measurement of temperature, and that branch is called thermometry. So thermometry is the branch of physics that deals with the measurement of temperature. And if we consider a device that is used to measure the temperature, we call it as a thermometer. So the two names, thermometry and thermometer. We have different thermometric scales like Celsius scale, Romer scale, then Fahrenheit scale, Kelvin scale, etc. This picture shows the temperature of ice point, that means the ice point, and a steam point. For example, in ordinary Celsius scale we have a 0 degree as ice point and 100 degrees Celsius as the steam point. In between there will be 100 divisions also. So in an ordinary Celsius scale thermometer we have 0 and 100, in between 100 divisions are there. In Fahrenheit the ice point is mentioned as 32 degree Fahrenheit, and the steam point is 212 degree Fahrenheit. In between there are 180 division. Similarly, Romer scale, 0 is ice point is taken as 0 Romer, and steam point is taken as 80 Romer, and that's divided into 0 to 80 is divided into 80 divisions also. Similarly, ice point in Kelvin scale is 273 Kelvin and steam point is 373 Kelvin, that is divided into 100 parts. And there is a relation between all these scales. You can use this equation, that is C by 100 is equal to F minus 32 by 180 equal to R by 80, that is equal to K minus 273 by 100. This equation gives the relation between all the scales and their values. It is seen that the size of a body increases when it is heated, and this increase in the size of a body when heated is called the thermal expansion. There are different expansion. One is linear expansion. As the name shows, linear expansion means there will be increase in the length of a body upon heating. For example, a metal rod you take, heat it, then its length will be increased. That increase in the length, that expansion is called a linear expansion. It is seen that you take a rod, a solid metallic rod of length L, then increase its temperature by a small amount, that is by delta T, just in given increase in the temperature delta T. Remember, delta T is the increase in the temperature. As a result, its length becomes L dash, a new length it is. So the increase in the length is L dash minus L. So the difference in the length, the expansion or increase in the length L dash minus L, depends on certain factors. One is it depends on the temperature rise, that is this increase in the length L dash minus L is proportional to the temperature change delta T. It is dependent also on the original length of this conductor. That means if you take already a long wire, if you heat it, it will expand much more compared to a small wire, a short wire. So using these two equations, let's arrive at an equation. This L dash minus L, that is increase in the length, is proportional to L and delta T. So it is taken together. So L dash minus L is proportional to L delta T. So here is a proportionality constant, and this constant is alpha. This is alpha. So this proportionality, we are replacing it with an equation. So there is a constant needed, and that constant is alpha. So if I take this L dash here, if I take all these terms here, this minus L dash I take to the right side, rest terms if I bring it here, so what happens is L dash becomes L plus alpha L delta T. Sorry, L dash minus L is equal to alpha L delta T. So L dash is equal to L plus alpha L delta T, or L dash is equal to L into 1 plus alpha delta T. This is L, here is L, so we take L outside, so L dash is L into 1 plus alpha delta T. So here is a proportionality constant alpha, and that constant is called coefficient of linear expansion. It depends on the nature of the solid. For different solid it will be different. And this alpha coefficient of linear expansion, from the above equation we can write L dash minus L by L delta T. This L dash minus L is the increase in length, that is a delta L. So delta L is increase in length divided by L delta T. So we can define this coefficient of linear expansion as the increase in length delta L per original length. That is, when delta L by L I am taking, I am getting increase in length by original length per unit rise in temperature. That is, when I make this delta T as 1, alpha is equal to delta L by L. That is what delta T is, the increase in temperature for unit 1 increase in temperature. When this is 1, alpha is delta L by L. That is what the coefficient of linear expansion alpha is defined as the increase in length per original length for unit rise in temperature. This alpha has a unit, and that unit will be 1 by Kelvin, because this is delta L expressed in meter. L is also expressed in meter, so that is cancelled, and delta T, its unit will be Kelvin. So 1 by Kelvin, Kelvin inverse is the unit of coefficient of linear expansion. Similarly, we have another term that is called superficial expansion. This superficial expansion is the increase in the surface area of a metallic body. So when when a metal is heated, its surface area also increases. This increase in the surface area is known as superficial expansion. So let's consider a metal sheet of surface area S. Its area is changed to S dash. Let it has a area S initially, surface area S, that is changed to S dash by heating it by a temperature through a temperature delta T. As we said previously, this increase in surface area is S dash minus S. That is proportional to the original surface area as well as the temperature increase. So considering these two factors, we arrive at an equation S dash minus S is proportional to S delta T. So replacing that proportionality with a constant, we introduce a constant beta. Previous case it was alpha, so here we introduce a constant beta. So S dash minus S is equal to beta S delta T. So we get S dash is equal to S plus beta S delta T. So this is our equation. S dash is equal to S into 1 plus beta delta T, where beta is called coefficient of superficial expansion. Previous case it was coefficient of linear expansion, so here it is coefficient of superficial expansion. And from this equation we can write beta is equal to S dash minus S by S delta T, that is increase in the area delta S by original area S into delta T. So here also we can give a definition for superficial expansion as when delta T is 1, this beta is equal to delta S by S. That is, coefficient of superficial expansion is defined as increase in surface area per unit surface. Increase in surface area by original surface area per unit increase in temperature. So we have discussed about two type of expansion. One is linear expansion, other one is superficial expansion. And the last one here is cubical expansion, that is, as the name shows, the increase in the volume of a body. For example, a metal block you take, heat it, its volume increases. So increase in the volume of a body is called upon heating is called cubical expansion. So as usual what we do is we take a body of volume V as the volume is changing. So let's assume a block of volume V that is heated by increasing the temperature by delta T. As a result its volume becomes V dash, a new volume V dash it becomes. So this, like the previous case, this V dash minus V, that is the increase in the volume, depends on two factors. One is the original volume and the temperature rise. So as in the previous case, this increase in volume delta V or V dash minus V is directly proportional to V and delta T. So here the constant of proportionality is gamma. We give a new constant, that is gamma. So as in the previous case, gamma will be V dash minus V by V delta T, and its name is coefficient of cubical expansion. And this increase in volume is delta V by V delta T. Here also we can give the same definition. Coefficient of cubical expansion gamma is defined as increase in volume by original volume per unit rise in temperature. So as usual, unit of this also will be Kelvin inverse. Now let us try to relate this alpha, beta and gamma, all the three. Let's try to relate. So for that, what we can do is we can take a body, a cube of side L, so that its volume is L cube. Upon heating, each side of the cube is increased. Each side of the length of the cube is increased, and the length becomes L dash. When there is a temperature change of delta T, this L dash is L into 1 plus alpha delta T. Already we know this relation. L dash is equal to L into 1 plus alpha delta T. So the increase in the volume, the new volume will be V dash. That new volume will be new length its cube. New length is written here. So its cube is what? A volume, new volume. So expanding this, we can take L cube. L dash is L into 1 plus alpha delta T. Substituting this, L will have a cube, that is L cube. This term also a cube here. This is a plus b, the whole cube format. So a cube plus 3ab, 3 into 1 into alpha delta T, plus a cube, for example, this is a and this is b, this term is fully b, a cube, that is 1 cube plus 3 a square b. So 3 is here, a is 1, its square is 1 itself, b alpha delta T, plus 3 a b square, 3 into 3 is here, a 1 b square, this full square, alpha square delta T square, plus the last term, this cube, that is alpha cube delta T the whole cube. Already alpha is very small, so this square terms and cube terms can be neglected. This term can be neglected. We'll take only the first two terms. So we get a V dash is equal to V into 1 plus 3 alpha delta T. So from that we can expand it and we can get gamma, which is V dash minus V by V delta T. We can get from this, what we can do is V dash is already here, this is V dash, this minus V divided by V delta T. This was the definition for gamma. So if I substitute this, I get V into 1 plus 3 alpha delta T minus V divided by V delta T. So from this we will get V is equal to V into 1 plus 3 alpha delta T minus 1 by V delta T. V and V cancel, 1 and 1 cancel, 3 alpha delta T by delta T, that is 3 alpha. Similar to like a volume is L cube, the error in that we have seen, many times we have seen error likewise 3 times it comes. So similarly gamma is 3 times alpha. Similar procedure we can do for this area S dash, which is S into 1 plus 2 alpha delta T. In the same way if we proceed, for example S surface area is L square, if you do L square term, but so new surface area is L dash square. L dash is L into 1 plus alpha delta T. If we follow this, S dash is equal to L square into 1 plus alpha delta T the whole square. Expand it, you get this term. Similar. So similarly if you follow, you get that beta is 2 times alpha. So the final relation between all the three, we will get the final relation, that is alpha by 1 is equal to beta by 2 is equal to gamma by 3. So this is the equation connecting all the three, alpha, beta and gamma.